All right, should we get started? Okay. Oscar, is the camera on? Yeah. Okay. It's gonna stay there like that, right? Okay. All right, everybody. So today's lecture is going to be about alternative consensus. So we've heard a lot about the different blockchains and how there can be different flavors of cryptocurrencies and blockchain platforms. Some of them might have different cryptographic hash functions. Some of them might be faster or more scalable. And a lot of that comes from the difference in their consensus protocols. So who remembers when I talked about how we'll have different distributed systems or different cryptocurrencies, and they'll have three components, right? So it'll be some way of managing the identity in this like distributed network, some way of storing the data, which in our case is most usually a blockchain, and then some way to come to consensus, so the consensus protocol. So you can kind of plug and play these three components and get like different combinations. So I think that alternative consensus is a really great way to kind of have different functionalities, and that's really exciting. So Brian and I really like this lecture, so we're teaching it together today. So we're going to talk a little bit about distributed systems in general, and that's because that's how we're going to study what a consensus algorithm really is and what we can do to make changes within certain parameters. Then we're going to talk about Nakamoto Consensus and different variations of that and maybe design our own consensus algorithm. And then we'll talk about proof of stake and some implementations because that's something that's very interesting and probably a lot of you are interested in. And then we're going to talk about Brian will talk about voting-based consensus and federated consensus. So first off, I just want to ask you guys, what are some blockchains or altcoins or cryptocurrencies that you know of? Just like shout them out. Ethereum. Tezos. Sorry? Ripple. Yeah, so there's a ton, right? I think all of these have their own blockchain. I might be wrong on maybe one or two, but some of them offer different consensus protocols. Like Purecoin uses proof of stake because they try to be environmentally friendly. Zcash is particularly privacy centric, and so is Monero. IOTA actually uses a different data structure. A lot of these have different functionalities, and consensus is often the thing that is different about them. So let's talk about distributed systems. So first, the fundamentals. A distributed system is going to be some network of independent nodes, and they each represent a process, and they do this process independently, and then they talk to each other via certain messages. And of course, there is no centralized control or node that they're all connecting to that they're getting all their messages from. They connect with each other independently, and it's all very peer-to-peer, as you would say. And their purpose is to accomplish a certain goal. So that's very vague. Some cases it'll be we want to keep track of who owns what amount of money. So that's in the case of Bitcoin, right? But there may be other goals that you have in mind. So some properties of distributed systems are concurrent components, so they're all working on their own thing at the same time, independently. They have message sharing, so they have to communicate with one another. It would make no sense for them to not communicate with each other, right, because they want to accomplish a certain goal together. There's no global clock. There's no central anything, really. There's no global anything. So what we mean by global clock is we wouldn't be able to say, like, oh, at this timestamp this happened. We can only say, relative to each other, this is what happened, because we cannot enforce any kind of central global thing of any sort. And there might be potential failure of individual components. So unlike a central system where it's just one guy and you can say like, oh, just be there all the time, there might be cases where a node might go offline or a node might be malfunctioning or a node might be adversarial. So they might do weird things that you don't expect. So the idea is majority opinion, general agreement. So what I mean by this is maybe not everybody comes up with the same idea, but in consensus, everybody has to agree ultimately on one thing, one value or one result or whatever it is. To come to consensus means to come to a 100% everyone agrees on something. So just understand that, maybe you'll have 50% voting on this or 75% voting, but at the end, everyone ends up with the same result. And why do we have distributed systems and why do we study them? So if you don't know this already, many problems cannot be solved by one computer alone. Or some things are just way too big, or there's data sets that are too large to store on one computer. There might be problems that take a long time to solve, so you might have parallelization going on. So in this case, we have aircrafts that cost hundreds of millions of dollars, and there's hundreds of passengers on this airplane. And so there are many different components that need to communicate with each other. So for example, you know, I don't know about planes, but let's just say all of these are different computers and they need to make sure that they communicate with one another so that the plane doesn't crash, right? And so realistically, you're going to have computers that fail sometimes. And this is a really big problem because if, you know, something fails and then the plane crashes, that's a lot of lives at stake, right? So we study distributed systems in order to have fault tolerance, and as well as other things. And we want to make a reliable system from potentially unreliable parts. And you want to create trust without trust, and that's why we study it. So this is very important. Let's say we're launching a rocket, or let's say we have a warehouse scale computing system with a lot of servers, and they need to you know, come up with answers together. So, and this is obviously applicable to blockchain. So are there any questions on fundamentals of distributed systems? Okay, yay, okay. All right, so some properties that we want to study when we are thinking about this distributed system communicating with one another. So the idea is all components are going to agree on the same state. That's consensus, right? I already mentioned that. Whoa, wait. Okay, so every node is going to, this is not the slide that I have seen before. So let's say each node starts off with a random value of 0 or 1. So how are we going to have all these nodes come to an agreement on whether we want 0 or 1? And how do we define the correctness of this system and the protocol that they use to reach agreement? So we have two different ways of categorizing the properties that we care about when we're looking at consensus algorithms. The first is safety. So this will not happen. This is basically if you were to draw a Venn diagram or some boundary of what can possibly happen as a result of this consensus protocol, this is everything that's outside of it. So let's say, for example, we have a distributed system where they're all calculating some value. And a safety property would be something like, oh, these nodes will never terminate with the incorrect output. So we're guaranteeing that something wrong will never happen. On the other hand, we have our liveness properties. So like the boundaries that I just mentioned, this is everything within those boundaries. So this must happen. So it's not only like all the possibilities that would happen, but something that must happen. So it's kind of a very tight bound on what can happen. So this would be every node is going to output a correct answer. So you say, I guarantee this will happen as a result of this protocol. Are there any questions on the difference between these two? It's pretty easy to understand. Okay. So the correctness of a distributed system is achieving its intended goal. So of course, the goal will be different in different cases. So usually it's just we agree on 1 or 0, or some variation of that. So to ensure correctness, to ensure that we achieve our goal, we use a consensus algorithm. So an algorithm usually can be applied to any kind of problem that you want to solve to reach some kind of goal. And so a consensus algorithm is specifically an algorithm that we use to come to consensus in a distributed network. And we have to achieve the following: validity, agreement, and termination. So validity is any value decided upon must have been originating from one of the nodes. So if I say 0 and you guys say 1, or some other people say 0, and our result is not going to be 2, right? It's going to have originated from one of our nodes. Agreement is all non-faulty processes will agree on the same value. So we've said this many times, you agree on one value. And termination, all non-faulty nodes must eventually decide. So we can't just be in this like circle saying, I want 0, I want 1, I want 0, I want. It's at some point going to terminate with something that we've decided on. All right, ooh, yikes. Okay, so now we're gonna apply this to the safety and liveness properties. So the safety properties are the validity and agreement. So this is the idea that we're never going to decide on some kind of faulty value or some trivial random value that we did not originate from or that we do not agree on. So you would categorize those in the safety category. And in the liveness category, we say termination. This will definitely happen every single time. The nodes will eventually decide on a value. Apologies for the slide. And so one clicker, okay, so first of all, any questions on these two types of properties and how we're categorizing them? No? Okay, cool. So I have a clicker question. This is something that someone said to me a while ago. He said one of A or B, and I was like, I don't know if you should think about it that way. So the question is, a distributed database has many copies of the ledger, while a centralized database has one copy, or two, or whatever it is, just centralized. That means it must be faster/easier or slower/harder to read and write from the distributed database compared to the centralized one. So do you guys want to maybe discuss amongst yourselves, and then if we have an answer already, like maybe we can go. Does anyone have an answer to this question? Yeah.
Wouldn't it be faster because if it was centralized one, then a node would have to first connect to centralized one, then write and rewrite them in the scheme. Whereas it's decentralized,
so your answer is that it is faster. Okay. Any other answers?
I would say it probably depends. Slower or harder would be my initial guess. There will be multiple states of the database, and you want to ensure you have the correct copy as it is.
Yes.
You want to check multiple times.
Yes.
Centralized one, you check once.
Okay. Anyone else have an answer? Very good answer. Yes. Okay, interesting perspective. Okay, so the way I want to answer this question is it really depends on what you want. Yeah, so if you are your own node and you control that database, it is obviously much faster for you to access your own database compared to some remote server somewhere. It might be only marginally faster, but it could be faster in that sense. But the way I also want you guys to think about it, so keep listening to the rest of my sentence, it could also be slower/harder because in a distributed or decentralized database, if you want everyone to have the same value, if you want to make sure that we all agree on a value before we decide that we want to read from it, then you might be waiting a while for the system to come to consensus and agreement on what the value is before you can read from it. And so in a centralized database, you only have to update one copy. And in a distributed database, you would have to update everyone's copy. Again, this is obviously if you want everyone to have the same value. So it really depends on what you want. And we're going to look at how we can make trade-offs in what we want in a consensus protocol. So we all understand why I said that was the answer to the question. Sorry that it was kind of a trick question. Okay. Cool. So any questions on distributed databases and how we categorize algorithms? Okay, cool. So the CAP theorem is, oh, yes. Oh, yeah. So sure. The question was, how can I explain what a node is? So you can think of a node as a computer. I suppose a computer could run multiple nodes as well. But definitely do not think of it as one person or one entity or one company or anything, because you can run as many nodes as you want. But this node is essentially going to have its own identity within the network. So it's going to be able to send messages. It's going to be able to compute processes. It's going to participate in the consensus process, everything. Yeah, it would be kind of like an account, yes. Yes. Cool, good question. All right, so now I'm going to talk about the CAP theorem. So the CAP theorem is a fundamental theorem for any distributed system pertaining to achievable properties that you can get from this system. So when we're designing a consensus algorithm, we want to keep this in mind because there are trade-offs that we can make when we are deciding on how we want this protocol to work. So it has 3 different properties. We have consistency, so every node provides the most recent state. So what this means is when you ask a node for the recent value of the network, let's say I want to know how much Bitcoin I have. This consistency with a consistent network would make sure that every node has the most recent value that everyone has already come to consensus on before then giving me that value. And availability means that anytime I query a node, it's going to give me a value. Right, so I can read and write whenever I want. It is very available to me. And partition tolerance means when you envision this distributed network, right, there's very many nodes. We cannot always guarantee that all of the nodes are going to be talking to all of them at the same at every moment in time. And so partition tolerance means that you're going to allow for different partitions in the network to happen. So the way to visualize this is, let's say, actually this room is a perfect example. So let's say we're all nodes in the network and we're all connected to anyone within 10 feet of us, right? So let's say this middle row right here goes offline, right? So the people on this side cannot really reach the people on that side just because they happen to be offline right now. And they can do that whenever they want because there is no one telling them what to do. There's no government saying you must be online at all times. So in this case, there would be a partition. Does that make sense? And basically, partition tolerance means that we are allowing for these failures to happen, or not failures, these partitions to happen. So we have these three properties, and you can actually only have two of the three, and I'm going to explain why. So that little like dot in the middle, that's like magical fantasy land. It doesn't exist as far as we know. Magical fantasy land. So let's say I have a network. This is a distributed network. Let's say there's only 4 nodes, but envision like a bunch like coming out of the left and right sides. And this network, basically, their goal is to keep track of my favorite color because it changes constantly. And so they always want to come to agreement on, what the favorite color is. And they have a consensus protocol. So let's say we have a consensus protocol. So let's say I tell them my favorite color is blue today. So let's say we have a consensus protocol that is partition tolerant and available, but it's not consistent. So I've told the people on the left side that today my favorite color is actually red. So it's not blue anymore, it's red. But there was some kind of partition that happened in the last few seconds. It could only last for just that second. But while this partition exists, I ask the right side, what's my favorite color? And they still think it's blue, right? And they're going to give me an answer right away because this is prioritizing availability over consistency, right? And this results from the fact that it's partition tolerant. So of course, it's not always going to be like this. It doesn't mean that it's going to be inconsistent all the time, but it just means that you're going to have cases like this that happen, right? So you cannot guarantee consistency all the time. So let's say we have a partition tolerant and consistent network. Those are our goals. And so we have a consensus protocol in which I am telling the left side, my favorite color is red today. Then I go and ask the right side, what's my favorite color? And they say, oh, I'm sorry, I don't know. Because there's this partition and I need to wait for the majority of my nodes to get back to me before I can tell you what your favorite color is. And of course, like I said before, it doesn't mean that the network is always unavailable. It just means that cases like these are going to happen every once in a while, and we have to allow for that. That makes sense? All right. And then we have the case where we want to be always consistent and always available. So anytime I want to query the nodes, it always has to give me the most recent state, and it has to give me an answer right away. So in this case, there's no, we can't allow for partitions because the whole network has to be talking to each other at all times. This makes sense? Okay. So in reality, this is not very realistic because we always have to be partition tolerant, and because we cannot always guarantee that all the nodes are going to be live, especially when we're all working independently. Now, of course, in a centralized database, you can say like, oh, I have 5 copies of this database. And I manage all of them, and I want to make sure that they're always consistent and always available. If I'm the only one managing them, then maybe that's possible. Maybe one of them goes offline at some point, but I can always get a majority of them. But in real life, if we're truly talking about a truly distributed database, or a truly distributed system, this is very unrealistic. That makes sense? Understand why. So really, we only look at partition tolerant and consistent or available networks. Okay, so the CAP theorem is actually really cool. So we're going to try to apply this to a consensus algorithm later, so keep this in mind and in the back of your head. All right, any questions on CAP theorem? So what does CAP stand for? Great. Very happy about that. All right, so how many of you have heard of the Byzantines generals problem? Cool. Good amount of you, actually. So the Byzantine generals problem is this idea that sometime in the Byzantine Empire at some point, there were a bunch of generals stationed around a city, and they have to coordinate an attack. But they're very far away from each other, or they have to send anonymous messages, or some kind of thing where there is no centralized person that's like, hey, you're going to attack or you're going to retreat. So their goal is to all do the same thing. So they all decide on either retreat or attack. So there's two values that are possible, and they're going to decide on that. So what they're going to do is they're going to send messages to each other, but there may be saboteurs among them that are sending false messages. So let's say, ideally, everyone's on the same page, so everyone says, like, yeah, let's attack, I'm ready to attack, you go. But then there's going to be some guy out there that says, oh, but the commander told me to retreat, right? And that would cause confusion. So it is not changing the slide. Okay, so my question for you guys is, let's say we have one trader, and there's 1, 2, 3, 4, 5, 6, 7 honest generals. Do you think it's possible for them to actually succeed? There's one trader and 7 generals. So 1/8 of the network is malicious. You think it's possible? Who thinks it's possible? All right, why do we think it's impossible? Anyone here want to answer? Because the vast majority is still honest, right? I'm not saying every time they're going to succeed. I'm saying, is it possible for them to succeed? Could we design a consensus algorithm for them to succeed? So the people over here who said it's not possible, please give me an answer as to why you think so. I was too lazy to raise my hand. Anyone else here want to give an answer as to why it would be impossible? Okay, so let's vote again. Who thinks it's possible? Okay. Okay. So you guys are still not convinced. So let's say the consensus algorithm was the majority of the people told you that we should attack or we should retreat. And so that's how we're going to decide. Let's say that is the way that we decide. So would it be possible then? Because you'd see all these nodes that don't even have contact with the trader, they would have the same value, right? And what about the nodes that do have contact with the trader? I mean, the majority of the messages that they get will still be consistent, right? So maybe it is possible for them to come to agreement. And if we applied some computer science to it and made an algorithm, like it would be sure it would work, right? So let's try again. Do you think this is possible for them to win? All right, okay, I got most of you. The reason I said this is, what about here? What if we have 2 traders?
In this particular diagram, you can only connect directly to the nodes you're connected to?
Well, you can connect to whoever you want, right?
Send a message to the general on the far left?
Yeah. Theoretically, it's just geographical distance. Maybe it'll take more time, but yeah, it'll happen. Yeah. So who thinks it's possible for them to win? This is a 2 traders and 1, 2, 3, 4, 5, 6 honest generals. So that would be 1 out of 4. Right? Yeah. 1/4 of them are traders. Is it possible? You think it's possible? All right. Cool. What about 3? Think it's possible? 3 out of 8. Who thinks it's possible? All right, we got some takers, optimists. Okay, cool. So let's think about it. So spoiler alert, if you have more than 1/3 of the node that is malicious, you're not going to come, not every time you're going to come to consensus. So there's no solution for 1/3 or greater corruption. That's how we're saying it. So the solution to all remaining cases, so if we were to design a consensus algorithm that allows for malicious or faulty nodes, that means that is called a practical Byzantine fault tolerant consensus algorithm. So when we say something is BFT, it's Byzantine fault tolerant, which means it allows for adversaries. All right, and so there's two different kinds of adversaries. So there's fail-stop faults, so nodes can crash or not return values. It can go offline, but this is detectable by other nodes. So let's say we have different computers, and mine is going to go offline for a while. If the algorithm allows for certain nodes to go offline for a while, then that means it's fail-stop fault tolerant. And Byzantine fault tolerance is nodes can do everything that they can go offline, they can do whatever they want, and they can send incorrect or corrupted values, be corrupted or manipulated or whatever. We allow for like evil people to exist, basically. We understand what this means? Yes, thumbs up. Okay. Yes.
Can you describe the difference between these two?
Okay, so fail-stop fault would mean that the node can crash, they can not return values, they can go offline basically, and you would be able to detect that. So it's very obvious if, let's say, your neighbor is not here today, which is true in many cases, right? But let's say Byzantine fault is when someone is like evil, and you wouldn't actually be able to tell because they would just be giving you wrong information. So let's say the person sitting next to you doesn't want you to pass this class, so they pass you all kinds of like incorrect information about blockchain to make you like understand things incorrectly or whatever it is. So this you wouldn't be able to detect sometimes. Yeah. And in many cases, so let's say we have the airplane again, and different computers are trying to compute different landing vectors, for example. And so one computer might go offline and they're not available, and you're like, oh crap, okay, I'll just have another computer do it. Right? Or you could have a computer that you're relying on to compute this landing vector for you, and it malfunctions, and it gives you the incorrect value. So a lot of times when they're designing computers like this, they would say like, okay, we're gonna have 3 different computers or 5 different computers compute this landing vector, and then if one of them is different from the others, we'll just take that as like a faulty one, and we'll take the majority.
That would be a Byzantine.
That would be Byzantine fault tolerance, yes.
What does a BFT look like in the context of blockchain?
Okay, so for example, in Bitcoin we have proof of work, right? And that is Byzantine fault tolerant because as long as not more than 1/3 of the, well, okay. Let me backtrack. That's harder to explain. So let's say we have a consensus algorithm where everyone basically tries to hear from as many people as possible, or as many nodes as possible, and takes the majority of that and goes with that decision. So in that case, depending on what you mean by majority, it could be Byzantine fault tolerant because like this example that I showed you, most of them are going to get the same answer from the majority of the people around them, so they are tolerant of having one trader there. Does that make sense?
So what would a Byzantine fault itself look like?
Oh, okay. Yeah, so let's say, yeah. So let's say I am a node on the Bitcoin network, and I am going to fill a block full of like either empty transactions or incorrect transactions that nobody is trying to spend, and I try to pass that off as like the network consensus of what the last 10 minutes of transactions were. So first of all, I might not win the race, and also people will look at my block and be like, dude, this has like faulty or like wrong transactions in it, so I'm not going to take that.
Is this similar to a big
Not necessarily. Usually on
Those are more complicated than just a typical adversary. Yeah. Yeah, yeah. Sorry, that was very like ineloquent of me. But yeah, like you wouldn't be able to pass off like wrong transactions in the Bitcoin network. Yeah. Okay. So that's like an example of Byzantine fault tolerance. All right, so to kind of draw the analogy here, we have the Byzantine generals problem and we have blockchain. So the Byzantine generals problem, they're separated by geographic distance. And that's why there's no way for them to just, come to agreement easily. And in blockchain, we have actually a distributed network. So we have generals versus nodes, and we have trader generals versus faulty or malicious nodes that could be trying to make blocks with faulty transactions. We could have nodes that are going offline sometimes, stuff like that. And then Byzantine generals problem, we have unreliable messengers. And in blockchain, you could have nodes that are dropping messages, not propagating them or broadcasting them to the rest of the network, or just clogging up the messaging system in general. And then in the Byzantine generals problem, you're trying to decide either attack or retreat. And in blockchain, you are trying to come to consensus on the history. So for example, what transactions have happened. We can see the analogy, how this applies. Okay. Any questions? Okay. So I'm going to move on to Nakamoto Consensus. So now we're going to actually look at different consensus protocols that are possible for us to achieve these goals. So remember, the goal can be anything from deciding on attack to retreat, deciding on 1 versus 0, deciding on the whole history of the transactions that have happened, or the output of smart contracts. So this is very much applicable to a lot of things. So Nakamoto Consensus is basically, the process goes like this. You elect the leader who, through some kind of lottery. And the leader is going to create the next block, and others will see this block and decide whether or not to include it in their blockchain. So that's kind of like step 1, 2, and 3. And okay, what about this lottery? So how do we decide, who's going to win this lottery? The idea is everyone should have an equal chance of winning this lottery, right? So in Bitcoin, for example, it's not the amount of nodes, because if you could make 1 million nodes, you would have 1 million times more voting power. So the idea is we have everyone having 1 ticket, or this equal amount of tickets. So there is some kind of resource that we're tying the raffle ticket to. So does that make sense? So to kind of make this more clear, in proof of work in Bitcoin, miners solve a partial pre-image hash puzzle. And this basically causes them to expend resources, so 10 minutes of their computer's computing power. And because they've consumed this amount of power, they get like 1 raffle ticket. Think of it that way, as 1 raffle ticket. And this is kind of a lottery to see who is going to give the next block. And after this block is published and broadcast across the network, people are going to decide whether or not they want it. So again, it's Byzantine fault tolerant, because let's say you won the lottery and you publish a block full of like crap or garbage. People can still decide to reject it. So it's Byzantine fault tolerant. So you see how proof of work uses energy as its resource, its scarce resource, to tie raffle tickets to. Okay. But I wanted to have this graphic because this is a graph of the energy consumption by country. And so you have Bitcoin in the middle, wedged between Austria and the Philippines. Both countries with many, many millions of people. So that's how much energy Bitcoin uses, which is kind of unfortunate, because if you think about it, they're just solving meaningless puzzles. So you get security out of it, but maybe it's not the best way to do so. So to kind of make this even more clear, this is 1 Bitcoin transaction. And if this was 1 Visa transaction, maybe it would be acceptable. But it's 100,000 Visa transactions. So proof of work sucks, basically. So we want to see other ways of coming to consensus. So how many of you have heard of proof of stake? That's great, most of you. Okay. So maybe think about, maybe you already know the answer, but how would we tie the resources consumed to the native currency? So in proof of work, we are essentially having people prove that they have worked hard. They've done a certain amount of work, and so they deserve 1 lottery ticket. So how do we have people use their currency to prove that they have done something and deserve one lottery ticket? Any ideas? Yes.
You put your currency into the algorithm as your stake.
Mm-hmm.
Technically, I don't know how it works.
Mm-hmm. Okay, so we have a starting point. You put your currency into the algorithm as stake. That's exactly what you said, right? Okay. Yeah, you're staking your tokens in here. Anyone want to add to that? Yes. Yes, yes, yes. So that would be staking, right? So not only are you putting some money in there, but it's potentially you could lose that money, right? Okay, any other ideas? That's pretty much the gist of it. So proof of stake, validators instead of miners, and they're going to lock up stake. So this is money that you can't spend while you're, staked up in this, and you're being a validator. So you have some stake locked up, and the whole idea is you're invested into this network. So you have incentive to behave honestly. So if I, spent $1 million to be a validator on Ethereum or some other cryptocurrency, there would be no reason for me to try to attack the network or do anything bad to the network because I have $1 million in there. Okay. And like you said, there are some cases where you would implement slashing if a validator does something bad. So for example, if they vote on 2 blocks, I'll talk about this later, but if they do something bad, then you would be able to just destroy all of the stake that they put in. So that's proof of stake. There's a more hardcore version called proof of burn. So for example, you could have another cryptocurrency that maybe doesn't have a set of reliable nodes to come to consensus on. So you could bootstrap Bitcoin as the consensus protocol. So what you would do is you would say, I want some Brian coin. So I'm going to burn some Bitcoin by sending it to an irretrievable address. And so I've proved that I've spent resources, I've spent Bitcoin. And so therefore I deserve some Brian coin. So this is like proof of stake, but you actually can't get it back. So it's like more hardcore. Okay. So what about storage space? Storage space is also a limited resource, right? Albeit maybe not as limited as money or energy, but you could argue that a certain amount of storage space is also a scarce resource that you could use to prove that you deserve a lottery ticket. So does anyone have any ideas on how we can use storage space to do this? Proof of space. Maybe you want to discuss? Spend more, yeah?
I don't know, but the idea of it occurs to me is kind of like along the same lines that we discussed before, having algorithms that algorithms can't work right. Maybe people need to have some value that they can query immediately. And so in order to be able to query some value immediately, you have to have a bunch of information to
Okay. I like that. Anyone else? Yes.
Maybe like the blockchain gives those information stored that they would then use later to solve a riddle.
Okay, so you're using information, maybe a large amount of information, to solve a puzzle later.
The more information you have, the easier it is for you to solve.
Okay, so then it would be dependent on how much space you have, basically. Okay, so anybody else want to before I? All right, so proof of space is a thing. And so the idea is you would use an amount of disk space. So the more disk space you have, the better to solve a challenge. So there are applications that use this where you would actually store files as proof that you are contributing to the network and therefore you have say in the consensus process. So that's also pretty cool. What about proof of elapsed time? So this is definitely something that is scarce, right? And definitely something that everyone has a limited amount of, and you wouldn't be able to fake. And this isn't something that money can buy, so this is pretty cool, right? Like, I have 24 hours in the day, and you have 24 hours in the day. There's no way I would be able to say, like, oh, I actually spent 20 minutes on this, because if only 10 minutes have passed, maybe, that's what I'm saying. So how can we use proof of elapsed time to show that we have spent resources and deserve a lottery ticket? Yeah.
What I don't get is if you do on this program, right, you for elapsed time or something like that, where you use some limit time.
Mm-hmm.
But since the person is not getting involved, that doesn't make sense.
Sorry, could you say that again?
What I don't understand is if we use a computer to process something, right?
Mm-hmm.
We're not physically doing it ourselves.
Yeah.
So we still elapsed time in our sense, or
Well, yeah, it would still be a computer that's doing this for you. But time still passes by for computers. Yes. Yeah, so that would be, summating the amount of time. Like each of my nodes spent a minute, therefore I spent 10 minutes. I mean, in a sense where that wouldn't be acceptable, if that makes sense. Okay, so maybe the implementation is kind of what is getting us stuck. So you could have trusted execution environments, so hardware that you trust can actually output a certificate of, yes, this hardware was running something for 10 minutes, or it waited for 10 minutes. Ideally, it's not actually computing anything, it's just waiting for 10 minutes, and it outputs a certificate that shows that, yes, this actually happened. So that would be your proof of elapsed time. Other ways of implementing this would be a verifiable delay function. So you could write, in software, you can write a function that basically does nothing but wait for 10 minutes. And that if you can prove that your computer actually did this, this could actually be a very good way of showing that you've spent resources, right? So it's a good idea in theory, but yes, in practice, perhaps it is different. Yes.
How would you determine which computer wins
Good question.
whatever?
Yeah. So it would be a lottery ticket. So ideally, it's somewhat randomized. So for example, it could be that while you are computing this block, you actually find a random number, or you run a function that gives you a random number, and that number is going to determine how long your computer waits for before it tries to publish the block. So sometimes you might get lucky and it gives you a lower number and you only have to wait a lower amount of time, and sometimes you might get unlucky and have to wait a longer amount of time. But ideally it would be random so that each person would be equally likely to be the first one to publish a block.
So within the algorithm, there's randomization of which node.
Yes. Well, in all cases, you have some degree of randomization, right? So in proof of work, for example, you're computing hashes of, your block as well as a nonce, right? So there's no way of, it's kind of random in the sense that you never know when you're going to actually find that solution. It really depends on what your input is. And so it is kind of random because everyone has different inputs, that you're going to get, a good distribution of people winning every time.
I guess my question is, in this version, is the algorithm choosing? Because in proof of work, the nodes are choosing. The nodes are determining if they win or not by just chance. Is that chance programmed into?
Yes. It would be within the algorithm. Yes. The degree. Yes.
This is not exactly how to solve the problem which we were addressing proof of work, which is basically idle resource expenditure, right? It's energy in that case, but here it's just idle capital investment. And the operator can just scale their equipment such that they're equaling the value of what the work's been.
Well, in this case, it wouldn't matter what your equipment is. It would just have to wait a certain amount of time.
Right, so they just buy like a million really small computers.
No. So this is a question that someone else had as well. where could you get a bunch of computers to each wait 1 second and add all that time together? So no, it wouldn't work that way. You would have to have some kind of certificate that contiguously this amount of time was spent.
Could you have a farm for this type
No,
of
that's the thing. Yeah, yeah.
Unless you create a bunch of accounts, and then you just
I guess, but I don't know. Yeah, you would still be spending like a limited resource, which is time, is the idea. Oh, I see what you mean. Okay, I see what you mean, yeah. I guess, sure.
because you're still spending as much as buying a bunch of cheap computers and
Yeah,
it's the cost of the
yeah.
capital.
Yeah, I see what you mean. Yeah.
So
it's probably more expensive to do that. And
I suppose you could have like very cheap computers that
yeah,
have
use-
enough room for like the
use
big
this,
ones out.
use the
Yeah.
costs for
Mhm.
capital, like,
Okay, I see what you mean now. Yeah. Oh well. Nothing is perfect. Any questions on Nakamoto Consensus? Yes.
So I just wanted to clarify my understanding of state.
Mm-hmm.
So you're saying that the validator with the most stable name, or the number of validator that has the most currency,
Mm-hmm.
is granted the voting power to add those new blocks to the ledger, right?
Mm-hmm.
And that, right?
Well, I mean, the amount of stake that you put in is going to be proportional to some kind of voting power. How it's implemented is different across different proof of stake implementations, but yes, that would be a correct way of thinking of, yeah.
So then, how does that help with decentralization? Basically, the validator with the most money, I would think, would always be allowed
Mm-hmm.
those many blocks.
Right. So I'm gonna go into this really soon, but yeah, there's always gonna be some kind of degree of randomness. Like hopefully you have a lottery going on where perhaps you would put more stake where you would have more lottery tickets. But just because you have more lottery tickets doesn't always mean that you're gonna win every time. So that's the way of thinking about it. Yeah. All right, so we learned about why proof of work sucks. And so the most immediate, or I guess best, well thought of solution to this would be proof of stake. So in proof of work, you have miners with voting power proportional to their computational power, which is in many cases how many ASICs you have and how much power supply you have to them. In proof of stake, you have validators instead of miners, who are stakeholders with voting power proportional to the economic stake that they have locked up in the network. So that's the gist of it. So you have to stake your tokens to participate in the consensus process. You cannot be a free rider and not spend any money and still participate. You have to have staked some tokens. And these staked tokens cannot be spent. In many cases, you can withdraw them later. But while you are a validator, your staked tokens cannot be spent, and you cannot move them. Voting power is going to be in proportion to how much you stake. So ideally, you have people putting in more and more stake to have more voting power. And slashing is something that is implemented across many proof-of-stake implementations, and it's the idea of destroying stake tokens to punish bad behavior. And this bad behavior can be any number of things. So there's punishment that happens if you behave poorly. And the main idea is someone who's invested in the network will behave in his best interest. So let's say you want to be the top validator. Let's say you want to have a very high chance of proposing the blocks or very high voting power. So you put in like $1 billion into the network. Well, once you have that $1 billion in the network and you might be punished for doing bad things, it's kind of a dangerous game if you're trying to do bad things to the network because you could lose that $1 billion. That's the main idea. Sockman, yeah. I mean, how would you redistribute it is the thing. I think that is sometimes the case as well, where if you can prove that someone did something bad, that you would get rewarded. Yeah. But yeah, it's just implementation. Yes. So there are various bad behaviors that you can do, one of which is going offline. So in many cases, you'll get slashed for going offline because that's not in the network's best interest. In some cases, you could be trying to vote on two blocks, two different blocks. And if someone sees that you've put your signature on two blocks, then they will say like, hey, that is not cool, and you will be slashed as well. That's two examples. Do you have your hand up?
Just going back to what he said, I would assume the reason why they don't redistribute coins is because that would incentivize other miners to unjustly identify a huge whale as like doing something fraudulent so that they could receive money for that. But yeah.
Yeah, I think in general I agree. So what Daniel said was if you have rewards for finding malicious behavior, you could be incentivizing things that you don't want to be incentivizing. Yeah.
If you just do that for the two block thing, specifically multiple signatures, trying to close multiple blocks, that then even if you can't all just you can't prove a whale, put a signature on two different things.
Yeah. Yeah. But you would be incentivizing, let's say, you hacking into their computer. And in a consensus process, we want everyone to be kind of working together. So we don't want to incentivize, like, node-to-node competition or, sabotaging.
If you don't redistribute, I mean, there's no incentive to search for that or report that.
Sure.
I think one way to know about it is if there was a good random way to distribute the wealth, then the person who reports back behavior might not be rewarded for it because it might have to go to like a pool where it goes to like the foundation that runs the network or something. But I think you bring up a good point about incentive. It's really dependent on like, what you're rewarding and how that reward will incentivize something.
That's true, too.
The idea that people are behaving badly on your network, so the money is inherently worth less if they're bad actors using this money. I mean, I guess you're getting rid of them.
So with current proof of stake blockchains, money just goes if the actors determine.
I don't know how all proof of stake implementations work, but as far as I know, that is what happens. Yeah. Okay. All right. So here's one implementation. So the TenderMate organization runs Cosmos, and Cosmos's consensus protocol is called TenderMate. So I'm just gonna say Cosmos and TenderMate kind of interchangeably because it's kind of hard to make the distinguishment. So in TenderMate, or in Cosmos actually, nodes will stake tokens to become validators, and then now we go into TenderMate, which is the consensus protocol. So a proposer will be selected round robin style, where you have a little bit more likelihood of being chosen as a proposer if you have more stake locked up. And this proposer is going to propose the block. Very simple. They're going to take the transactions and put them into a block for you. And then they're going to broadcast it. And there's actually 2 more steps to it, but basically the block is going to be committed if 2/3 majority of the validators vote on it. So they sign up on the transaction, they've deemed it acceptable, and they've checked all the transactions, and they agree that this is going to be the next block. And so you only need 2/3 of the people. And so the nodes are going to wait for 2/3 of their peers to get back to them on what the result is before they actually proceed. So they're actually going to make sure that they're consistent. And the slashing that happens is going to be for bad behavior if you vote duplicitously. So if you vote on 2 blocks at the same height, you're going to get slashed. And if you go offline, you're going to get slashed. So I just wanted to mention that as their implementation. So maybe take a look at this slide. Let me look at what the time is. Okay, yeah, so never mind on that. If you have questions on how TenderMate works, like, just ask me. So I have a clicker question for you guys. Now we're going to apply the cap theorem that we just learned like half an hour ago. So what trade-off between consistency, availability, and partition tolerance are we making here in TenderMate? I have like all the relevant information at the top right there. Yeah? Yeah, we're getting partition tolerance because I did mention that it is okay for a node to go offline even though you will get slashed. All right, so we have partition tolerance. And then do we have consistency or availability? Consistency. That's the answer, consistency. Yeah, so TenderMate actually says, like, yeah, we prioritize safety over liveness or consistency over availability. So there's a line that says you're going to wait for 2/3 majority before they actually proceed. And that's written into the protocol. Yeah. And so my second question is this consensus algorithm Byzantine fault tolerant? Who thinks yes? So if people think no, please, if anyone wants to explain, yes.
Byzantine fault tolerance also kind of, does that definition include the fact that if working for the network conditions after it's stall availability indefinitely?
Yeah, so
Is that the same problem?
Byzantine fault tolerance is up to 1/3 of the network. Yeah, because there is no solution for there being more than 1/3 malicious. Yeah, so we call something Byzantine fault tolerant if it allows for up to 1/3 of the network being malicious. Yeah. Okay. So who thinks it is Byzantine fault tolerant? All right. Cool. So if you don't think so, please explain. Okay. Okay, cool. So it is considered Byzantine fault tolerant because you're doing a 2/3 majority of the vote, and the idea is unless you have more than 1/3, you're going to be able to come to a good majority every time. Yeah. And so can we also see like the other properties that we learned about consensus? So we want to have validity. So the accepted block is going to be one that was proposed by someone, right? So it originated from one of the nodes. We have agreement, which is we all decided on one block together. What was the third one? Termination. So at some point we're going to reach consensus. Yeah. All right. Cool. Let's move on. And so in Cosmos/TenderMate, we also have what's called delegated proof of stake. I think they actually call it bonded proof of stake, but you can also call it delegated proof of stake. And so in delegated proof of stake, the idea is maybe it's very costly for you to maintain a node that is validating blocks, and you don't want to do that, but you still want to put your stake into the process of maintaining this network. And so you can delegate some of your stake to a validator, and that would thus increase their voting power. But of course, the punishments also apply to you. So if they get slashed, you get slashed too, and that is very important because you can see how it would be a problem if you're only punishing one portion of the validator pool or whatever. And what's cool about TenderMate is the process of switching delegated stake. So if you want to switch your delegation from one node to another, it's instantaneous. And this is very important for avoiding centralization. So for example, if you are delegating your stake to someone it should be very easy for you to switch, because as soon as you detect malicious behavior, you should be able to switch right away. So this is one way of preventing or discouraging centralization. So one note on delegated proof of stake, it can also mean that you have token holders, so this would be Lisk's implementation, is token holders voting on delegators to propose blocks. So there's different definitions to proof of stake, but generally the one that you should use is the one on top where nodes delegate stake to other validators. Cool. So the difference between delegated proof of stake and proof of stake is just that you're able to delegate to other validators and pool in your money to do so. Cool. All right. Another implementation of proof of stake that isn't quite live yet would be Casper, and this is Ethereum's kind of research into how they would implement proof of stake. So the notable one I would say is the Casper the Friendly Finality Gadget, which is Vitalik's, versus Casper the Friendly Ghost, which is Vlad's. And so the way that Casper the Friendly Finality Gadget works is it's kind of a hybrid between proof of work and proof of stake, where you usually use proof of work, and then every 50 blocks you do a proof of stake checkpoint, where validators are going to validate all of the blocks that happened. And you're going to reach some kind of like finality threshold there. Okay. And so Ethereum is kind of in the process of switching to proof of stake. So what I'm guessing is that they want to roll it in slowly. I don't know the exact status on it right now, but the idea is that the switchover should happen at some point. So I have a kind of clicker question, but also kind of a discussion question. So what are some advantages that you see of proof of stake compared to proof of work? I'm sure there are many that you can think of. And what are some possible downsides that you see of proof of stake? Maybe just discuss with your neighbors, talk about it a little bit.
As their money builds, like inequality, as their money builds, they make more money, as their returns are exponential. Whereas someone who doesn't have their own money, way outside. This is like classic, wealthy, like poor versus
Like,
same. They both.
I've never been so like so crappy today. I don't know, I just like can't speak.
If you did, the same attacks that you could but if you think 1%, then the majority of everything is saying that your thing is probably. But I need this problem still. I don't get that. Yesterday, last week we were 1%. Now we're talking about Validators. No idea. What we talked about last week was that we mentioned. So we're just assuming it was like exactly. And 50 bucks. So why are you talking about? Is it?
Okay, what do we think? Yes.
I guess we'll start with that. If you have a lot of coins in proof of stake, your returns on capital are like exponential, whereas like people with not a lot of money are going to make less money. So it kind of like exacerbates the inequality within the system,
Right. Right.
and it kind of doesn't solve any of the problems that we have in society.
Okay. Inequality. Anything else? I'm sorry I'm not like exciting today. Anyone? Yeah.
It's hard to argue the value of the proof of stake. It's not the case can be made, but I think it's easier to argue the economic side. We have the examples behind it.
Hmm.
You're actually using some economic resource continuously, so there's investment. One thing I'd like to add on to that, or like argue against that, is in proof of stake you have you can design incentives to punish bad actors. So you can incentivize certain behaviors versus in proof of work everything's like there's no specific like punishment for anything that you do. But in proof of stake you can design protocols or like specific protocols that you can punish bad actors in the system. So that's just one thing to note. The stacking mechanism is there for punishment.
Yeah, and I'm
generate value. I mean, it makes people behave honestly, more honestly than they would in typical. Theoretically.
Why is that necessarily true?
Because all their money can be liquidated if they decide to like, risk being fraudulent. If they have more influence and more money, they decide to be fraudulent, then more money is at risk. Yes.
I understand what you mean, but how does that contribute to how much, let's say, this coin is worth? Like how much the coin is worth? Just because we are not allowing people to do that stuff.
I'm not arguing about like the value of a coin. I'm just saying that you could make your network more honest than let's say a different network that doesn't tolerate that's just what I'm saying. No, I'm not saying anything about the work of the coin at all. Like your consensus mechanism should not dictate how much your coin is worth. I don't think that's a particular good metric for the coin value. Your consensus protocol should dictate the value of your coin.
What do you think should be take value?
I mean, I don't have any insight on what dictates the value of a particular currency, but I mean, like a technical implementation shouldn't justify the cost or the value of it. That's enough.
Well, it's not the like the protocol itself. It's like investor confidence in the utility of that protocol.
Yeah.
That's the argument.
anyone else? Okay. So some arguments for why proof of stake is better than proof of work is that it's more environmentally friendly. So you're not wasting computational resources. It's not necessarily how much computers you have or all that stuff. It doesn't rely on meaningless computation. Another one is scalability. So you could theoretically have more transactions per second if you use proof of stake, theoretically. And security, so it would, in some cases it would be more expensive to reach 51% stake than it would be to reach 51% computing power. So that obviously depends on how much money is in circulation and how much the currency is worth. But in some cases, it would be more expensive to launch a 51% attack. And it is arguably more decentralized because you cannot have mining pools. Of course, you can have delegators give stake to different validators, and that's one form of centralization, but you can argue that is more decentralized. And so those are some of the arguments for proof of stake. But like Daniel mentioned, there is this problem of the rich get richer. So let's say you have the most stake in this network. And you are validating the most blocks, and therefore you are getting the most mining rewards. So that inequality kind of gets more and more exacerbated as you are getting richer, and people with less stake are unable to have as many block rewards as you. So it doesn't solve society's problems of inequality and all that. So this is a con of proof of stake. Any questions on proof of stake? Yeah. Initially distribute. So you could have mining rewards. So each block would create new coins. The first distribution. One of the. Oh, I guess that is true. I see what you mean. That's a question that I don't know the answer to. Yeah, so I guess in the case of Ethereum, when they switch to proof of stake, there will be people who already have Ether. So I guess I never thought about that, but yeah. Well, it depends on the implementation. Yeah. Mm-hmm. Mm-hmm. Mm-hmm.
Actually, in proof of stake, when you think about it, and it's not necessarily all the. When you're voting, on like a particular block, it doesn't depend on all the supply in the entire currency. It's just in that voting round specifically. So, because each round requires a new, or each block requires a new voting round. It's just depending on who's available as validators, and they take up tokens in that sense. So someone who has like, if no one's voting in a particular round, and someone who happens to like stake tokens, they might have like a larger probability of winning that voting round if no one stakes in that voting.
The proof of work does not have the reach that it should.
The rich get richer problem? You could say that it does, because the more basics you have, the bigger mining pool you have, the more block rewards you get. So that also has that problem. Yeah.
But you have to put in an estimate, so it's not like it's easy to do that. It's a lot harder to do that.
Yeah. So I guess the main theme is that you have a lot of trade-offs when you have different consensus protocols. So in proof of work, I said that it sucks, but it's worked so far and it's very robust. It's been doing quite well for the past 10 years, so we know that it's secure. On the other hand, proof of stake has all these great promises. Theoretically, it's like awesome, but we don't know if there are things that are wrong with it as well. There are fewer implementations of it, so we just have to see. Yeah. And then Brian's going to talk about more as well. Yeah. So really sorry that this was like terrible. I'll do better next time.
So I think my section will be a little bit shorter, but we talked a lot about Nakamoto-based consensus. This really assumes like there's no trust in this network. That's why you have to sacrifice resources to in order to like prove that you are somewhat trustworthy. But how did people come to consensus in distributed systems before this entire blockchain craze? So distributed systems have existed way before Bitcoin came along. So how did people come to consensus then? So before we start, we've been talking a long time, and so let's just take a quick breather and look at some nice images. So these images are from an island in Greece called Paxos. It's located off the western coast of Greece, and it's famous for its wine, and it's home to a lot of like sandy beaches along the Ionian coast, right? And so it's a popular yachting location. But the cool thing about Paxos, it's a Greek island, but it's also a consensus algorithm. Wow. Okay. So it was invented by a really smart guy named Leslie Lamport in 1989, not 18. And this guy's really smart because he won the Turing Award, so you know he's smart. And he's also responsible for like discovering or like coming up with the Byzantine generals problem. He's the one that like formulated and stated it. He likes telling stories, if you can't tell. So Paxos spawned off like a large family of consensus algorithms, but we'll focus on like the most basic version of Paxos. So the reason why Paxos is named Paxos, Leslie Lamport comes up with like a story on its particular like scenario of use, basically. So he titles his paper, not white paper, Part-Time Parliament. So in the story we have the island of Paxos, and we have this Paxan parliament that passes decrees and makes sure that everyone on the island is in consensus with these latest laws or decrees. And so the reason why it's part-time is the legislators are also known for leaving quite abruptly and attending like banquets or also like other outside activities. People have their own lives, right? No one is willing to remain in like the parliament chambers all the time, and they also don't have like secretaries to record everything, so they actually maintain a ledger recording everything that has happened. So the three types of legislators that exist in this Paxan parliament is a proposer. These people champion the requests of the citizens in the island, and they bring new bills to the parliament. We have acceptors, which are people who discuss and vote on legislation, and we have learners who learn the consensus result from this like a voting process, and they carry out the bill to everyone on the island. And so we also state another definition, quorum. It's any majority of acceptors. So one thing that we have to note here is that in this Paxos algorithm, there's a degree of trust amongst everyone already. It's not completely trustless like in a Nakamoto-based consensus algorithm. And so this protocol proceeds over like several rounds, and these rounds have two separate phases, a prepare and an accept phase. So the way that it works is first the citizen will talk to this proposer and say, like come up with a like particular decree or a bill. And then this proposer voices his like decree in the parliament. And so these decrees or these bills can be something like, oh, painting on the temple wall is forbidden. The sale of brown goats is permitted or not permitted, basically. And in the parliament, all the acceptors decide on whether to accept or not accept this like proposal. And so if a majority come to an agreement, then that decree is passed or that bill is passed. And at the end of that, the learner will talk to its citizens and tell them what has been like this latest bill that has been passed and why people need to comply with it. And so this matches a lot of the database systems or the distributed systems that are used in distributed systems. So a legislator acts like a server in a distributed setting. The citizen is like the client program that talks to these servers and requests values. And the current law is basically the state of the database. And so in the real world, all these cool companies use Paxos to maintain data sets or maintain distributed copies of their data. But one thing to note, very important thing to note, is that in this protocol, it assumes that there's a degree of trust in this network, and so nodes don't try to subvert the protocol, meaning that messages are delivered without corruption. No one can tamper with messages. And so in other words, we can see that this protocol, this consensus algorithm, is only fail-stop. It doesn't tolerate Byzantine failures where messages do get corrupted and people are being malicious. You can see that in the case of like these companies maintaining like their distributed data sets. All they have to they control all their data, and they don't have any adversaries within their own network. So they only tolerate failed nodes. But in practice, it's also really, really fast, and it's used to replicate large sets of data. But one thing to realize is that the original way it was defined, Paxos was really, really hard to understand, even for experts. So even despite like multiple clarifications from Leslie Lampour, people were still like, yo, this is actually just way too difficult, way too complicated, way too much overhead. So in 2014, an alternative to Paxos was created called Raft. Their goal was to create a more understandable consensus algorithm. And so in the Raft paper, it was titled "In Search of a Understandable Consensus Algorithm." And it also pokes fun at Paxos because, in theory, like this Raft is used to escape the Greek island of Paxos. So it's designed to be much more understandable, and it implements a leader-based approach. It's a little bit easier to implement too, and what's really cool is that JP Morgan's Quorum, which is a fork of the Theorem network, they substitute their proof-of-work mechanism in Ethereum with this Raft-based consensus. And so just a little bit about how it works. I don't want to get too in depth. So we have this elected leader that communicates with this client. So this client only talks to this leader, and the leader is responsible for communicating with all the other nodes in this distributed system and making sure that all its messages are being replicated on these nodes. And so this leader continues to lead until it fails. So like if it goes offline, a new leader is selected. So that's why there's a leader selection protocol, or a leader election protocol where the leader sends heartbeats to all its nodes. So once its other nodes in the network don't receive heartbeats anymore, it knows that the leader has died or gone offline. So a new leader is elected. And so the log replication is just basically, it makes sure that all the messages in this distributed system are being replicated and maintained. And so there is a cool info or a animation of how Raft really works. If you click on that link, we'll link it on the website or in Piazza. But this is to show off how Raft really works. Any questions? So these are two voting-based protocols. But one thing to really note is that these two protocols or these two consensus algorithms do not tolerate Byzantine faults. So they assume that all the faults in the system are fail-stop only. So that's why we're diving into a little bit of PBFT, which is the practical implementation of a Byzantine fault-tolerant consensus algorithm. And it was defined by Miguel Castro and Barbara Liskov back in like 1999. The cool thing about it is it's fast, and at the time, it was only 3% slower than the current like non-Byzantine consensus algorithm at the time. So that's really interesting. It was like a file store kind of protocol that was being used by I think it was Oracle or Sun Microsystems was using that as like the data store like writing kind of mechanism. And so this was only a little bit slower like 3% slower than that non-Byzantine fault-tolerant version. And so this is just an example of how Byzantine fault or practical Byzantine fault tolerance works. So we have a client that communicates to this distributed system, where we have a primary node, so let's say Jillian, that it communicates with directly. So I send a request to Jillian as the primary node, and she communicates with the rest of the nodes. Well, let's say, so this example isn't that great. It doesn't illustrate how it tolerates Byzantine faults, but it does show the example that it does tolerate a fail stop. So let's just say Nadir over here goes offline because of a spotty internet connection, because Comcast isn't great. So what Jillian does, she sends a pre-prepared message to all the other nodes in the system. Nadir should receive it, but if he's offline, he won't. So Alan and Gloria will receive this pre-prepared message, and they'll both send back like acknowledgments and prepare messages back to everyone in the network. And once that has been done, everyone will send these commit messages to one another, and if everyone has like an agreeing value, they'll all send it back to the client. The way that it's Byzantine fault tolerant is you calculate that based off of the number of messages that it receives and if they're different or not. I won't go into the details because it will get pretty complicated, but the idea is we have this like 3 different stages. A pre-prepare and a prepare and a commit stage. So we showed that the client talks to one of the primary nodes, and the primary nodes sends pre-prepare messages to everyone, and they all decide on a particular value, and they respond to the client. Any questions? And so naturally we've talked about Nakamoto Consensus, which assumes no trust in the system, and voting-based consensus protocols that actually do assume some degree of trust in our networks. How do we bridge those two together? So federated consensus is meant to bridge those two. What if we want to have a robust consensus mechanism, but we still want to be able to include everyone in this consensus process? So back to distributed systems, a quorum is a set of nodes that's sufficient enough to reach agreement. In Paxos, it was a majority. In a general setting, it's a set of nodes that's sufficient to reach agreement. And so what happens if we don't trust certain nodes in this quorum? How can we still achieve consensus? So our goal is how do we come to consensus? But how do we choose these quorums in a decentralized way without anyone, like a trusted third party, dictating who to trust, basically? So the idea is to introduce these quorum slices, which is a subset of a quorum that's enough to convince a particular node, let's say me, of agreement. So people can flexibly like dictate who to trust and how to trust people. And so let's say I'm this purple node on the very, very left, and let's pretend I don't know I'm colorblind, but I say, hey, this crayon is red. And then, but my peers on this right, the people I trust wholeheartedly, they tell me, yo, it's actually green, it's not red. And I go, okay, you just convinced me that this crayon is green. So I will update my like knowledge of the crayon that it's green. And so we come to consensus. Cool, right? And so the idea is we want to join as many quorum slices together so that we can achieve an overall consensus. So we use these quorum intersections that will form larger and larger quorums so that our entire network can come to agreement. But one caveat is if we have disjoint quorums where they don't trust each other and they have differing values, we can't come to an agreement in that case. So let's go through an example. So let's say me, Gloria, and Nadir want to go get lunch. And I suggest, let's get pizza. And so Gloria and Nadir they know Pappy's and they sell burgers for really, really cheap. So they go like, yo, it's only $1 for a burger today. So let's actually just get burgers. So I have a quorum slice with these two individuals, and that's enough to convince me to change my mind. So I say, okay, cool. Burgers are really great. I will change my decision to a hamburger. And so let's say Alan over here sees our group going to Pappy's and says, "Hey, can I join?" But he doesn't necessarily trust me, and so he forms a quorum slice with Gloria and Nadir, like this, and they convince him to get hamburgers. Really cool. So now we have 4 people going to Pappy's to get hamburgers. And let's say Oscar over there wants to come along too, but he doesn't know Alan or he doesn't know Nadir, so he doesn't necessarily trust them. So he says, "I only trust Brian and Gloria at this current point." So we form a quorum slice with him, and we convince Oscar to also get hamburgers. So we notice how we have now 5 people going to Pappy's and getting hamburgers, but we started off with only 2 people. And so the beautiful aspect about like federated consensus is you form like federations that you do trust, and you slowly integrate more people into your overall quorum of consensus. So decentralized control, so there's no one dictating what consensus to be reached, and it's also very low latency. This is an implementation detail, but it's also flexible trust. So if you don't trust people in a particular network, you don't have to trust them. You only specify whoever you want to trust, and that's really powerful. So what uses federated Byzantine agreements? So Ripple, which is a real-time gross settlement exchange and a remittance network, they use federated Byzantine agreements to achieve consensus. So it's a distributed ledger across a lot of financial institutions, and the idea is that these financial institutions can state whoever they want to trust, which banks that they want to trust, and they can come to consensus really, really fast. And so naturally it's a permission ledger because it's only big financial institutions like banks. So this is a little bit about like the topology of the Ripple network. We have validating nodes and we have like tracking nodes that maintain the ledger basically. But Stellar is an entire fork of Ripple actually, and their focus is not only to just connect big banks to a consensus protocol. They want to open up like this network to just more individuals than just banks. So banks, nonprofits, and just anybody in general can participate in the Stellar consensus protocol. So it's an open source protocol for exchanging money, and they're focused on distribution of wealth. They use federated Byzantine agreements to achieve their goals and maintain their state of the ledger. And so they use this example to explain how the Stellar consensus protocol works of like the lunchtime consensus that I explained below before. And so that's how like federated Byzantine agreements work in their consensus mechanism. And if you want to read a really, really neat comic strip, Stellar has a comic strip for understanding how federated Byzantine agreements work, which is really cool. Everyone good? Any questions? So yeah, there's a lot of like interesting readings on these topics. If you want to learn more, I'd highly recommend just reading the comic if you really, really want to, because it's interesting and it's fun. So yeah. So next. There's no quiz today, but we have a mid-semester feedback form if you want to fill that out.